This question is about a parallel beam of electrons all traveling at the same speed is incident normally on a carbon film. The scattering of the electrons by the film is observed on a fluorescent screen as illustrated in the figure 7.1. So here's a structure. We can see that a beam of electron is coming from the left hitting a carbon film. Be careful, it's a carbon film, so it's a two-dimensional structure and it hits the fluorescent screen, and it's a screen which is also a two-dimensional structure, so we can consider them as rectangular boxes. So the first part of the question says that assuming that electrons behave as particles, predict what would be seen on the screen. So if electrons are the particles, they can just simply straight pass through that carbon film and hit the other side on the fluorescent screen, so we get a uniform distribution right near the center, which we can write as uniform distribution around the center point. The statement B says, in this experiment the electrons do not behave as particles. If they do not behave as particles, they are going to behave like waves. So describe briefly the pattern that is actually observed on the screen. You may draw a sketch if you wish. So we have already mentioned that it's a carbon film and fluorescent screen is a two-dimensional structure, but first we consider that if it's simply a straight line and we have the atoms in the carbon will behave like a double slit experiment or like the multi-slit experiment. So what happens when a beam of electron passes through it? It diffract. So if we only consider the vertical slit, it's spread like this. But in a film, atoms are not just arranged in vertical direction, they are arranged in all three-dimensional directions. So we consider a horizontal distribution of atoms as well, which will also act like a multiple slit experiment, but in a horizontal direction. So this horizontal array of atom will act like a multiple slit in horizontal direction and diffract the diffract the incoming electron, which are behaving like wave along the horizontal axis. So we get these spots. So if we combine these spots, and actually it's not just in these two directions, it's in all the 360 degrees, along all 360 degrees. So if we connect these points, we get a circle. So that's the circle formed by the first order diffraction. If we have another, like a second order diffraction, we get another circle around it. So that kind of what diffraction pattern we receive on the screen. So these are the concentric rings, right? So we have to describe briefly the pattern, is right. So these patterns are concentric rings due to the diffraction from the array of the atoms. So that's how we can answer the question, and those are actually, if we draw it here, so that's the pattern, the concentric rings. If we look from, depending, the center one is a zero order, that's the first order, and that's the second order, and we will get more and more in how many order of diffraction is possible due to the spacing and the wavelength of electrons. Now the speed in the part C, the speed of the electrons is gradually increased. State and explain what change, if any, observed in the pattern, the circular pattern which we observed on the screen. So as we increase the speed, wavelength is lambda equal to h over mv. So as electron has more speed, their wavelength is smaller. So if wavelength is smaller, diffraction will be less. So the spreading of the circles or the diffracted pattern will be less, and they will be concentric circle with smaller radius, because this time the diffraction will be less. So we can write here greater speed, smaller wavelength, less diffraction. So due to that, smaller radii rings.